Oops. Hopefully I'll even be more coherent.
Okay, folks,
So today what I'm gonna do is I'm gonna start quickly by passing back your exams. I do not want them back, so they are yours to keep. I plan to get the answer key up over the next day or two. Then I want to quickly discuss Blackboard grades as well as progress reports, which I've submitted. Then I'll get into a brief discussion, very brief, about the labs, and then the bonus, and then we'll get into a discussion. I want to quickly just confirm what I understand from Dr. DeRocher's notes about last Thursday, and then get into the new material for today. So that's kind of my thought process for today. So first of all, with the exam, when you get your exam grade back, there will be numbers on the back of the exam. The first will be how many points you missed. The second will be how many points out of 125 you made on the exam. And then just so that you can understand what the percentages were, I went ahead and put into percentage for the third number. Overall, the grades were, I don't even know what the general average was, but overall the grades were fairly good, but I do have some grades that were not as great. And I wanted to remind those individuals that I do drop an exam grade. However, they tend to get tougher from here. So if you did poorly on the first exam, you need to come see me. Let's talk about a plan of action to get you back on track so that you can pass the course. Which brings up the progress, the Blackboard grades and the progress report. Other than the lab you did on Thursday of last week, I think I've got all the grades entered in already. So I'm trying to stay on top of things. I do have to put a homework together for today, so I'll do that when I get back to my office. But I'm trying to get back on top of all of your grades. I'll pass back the exam grades in class, but I'll pass back the labs in lab today, on Thursday. So, but you can already see your grade from the spectroscopy lab, and I hope to get the other one graded. Now, when you look at your grades on Blackboard, there is a total column. That total column is assuming drop grades. So you've only had one test. So right now it's dropped that test grade. Even if you made a perfect 100, it's dropping that test grade because it doesn't know because right now that is the lowest test grade. It's dropping your lowest lab grade already. Now what that means is if the next test or the next lab is higher, then it's going to change or it's lower, it's going to change everything. So it's automatically going to reflect the drops. Therefore, that thing really won't be accurate until the end. Because it's going to be constantly changing depending upon how you score on it. So keep that in mind. Now, that being said, when I did do the progress report, since I don't know what's going to be dropped for certain, I went ahead and just added all the grades together. So you may receive a progress report, and the ones that will get a progress report are those that have currently a D average or an F average in this case. And the reason I choose a D is because in order to go on to college Chem 2, you have to have C or better in the class. So that's why I also give a progress report to those that have a D. So anybody with a D or an F, they will be receiving a progress report through Navigate. And it's because I've included all the grades. And you could have done okay on the test, but not been turning in your homework, and it could drop you. So we got to look at what's going on per person. It's on an individual basis. Questions about those things I mentioned so far? I've kind of lumped all three of the top three, or all of the top three into one conversation. The other thing I do have up there is another bonus opportunity. I don't have a good way to put this into Blackboard. Well, I guess I can. I can put the flyer in there. On Thursday during the X period in the other large lecture hall, the one behind us, Angela Grayson will be here. She is a patent and intellectual property rights lawyer. To be a patent lawyer, you have to have a hard science degree. In other words, you've got to have a science degree to be a patent lawyer. And she's going to be here to talk about being a patent lawyer and intellectual property rights. Now, the reason she's coming in is because she got a bachelor's in chemistry and a master's in chemistry, and then she went to law school. So it's just showing different paths that a person can take that maybe that suits them more. So we've got her coming in, and if you attend, it's a 5-point bonus for attendance. I will be here, and I'll be looking for you to participate, just like I did on Zoom. Questions? Oh, which brings me back to Blackboard grades. I did go ahead. I don't have the list of individuals that attended the political science talk in person, the Science Wednesday over politics in person yet, but I've included all of the other bonuses that I've received thus far. So there's now a bonus column, and I'll just keep adding to the points up to 30. Questions? So let me get you your test back in. And I'll get the sign-in going while I'm doing that. Junior Acosta. Alexis Altamirano. Channing Babb. Lauren Carrick. Marissa Carson. My ear itches. Cassia Cobb. Jerry Coleman. Malia Cook. Bailey Daughtery. Lauren Irvin. Olivia Farnsworth. Anston Glasgow. I think. Aniston. Ariston. That looks like an N to me. Sorry. I'll learn. Emma Graham. Michelle Hall. Sunny Harrington. Rachel Keys. Eli Lyles. Kaylee Martin. Jalal Masood. Hannah Mowry. Sarah Nance, Brislin Oden, Jared Palmer, Emma Caserb, Evan Perkins, Kara Ponder, Simone Quills, Jennifer Resendez, Michaela Russell, Will Sandifer, Gabrielle Stovall, Liam Taylor, Tavis Taylor, Jelaine Tyndall, Destiny Turner, Amanda Walsh, Madeline White, by the way, the most missed question on the exam was probably, make sure I have the right exam. Question number 3, part, the first column. Now, you didn't do as, this class didn't do as bad as my other class, but protons determine the identity of the element. Neutrons determine the isotope of the element. And electrons determine the reactivity of the element. That is what they are responsible for. Yes, protons are positive, electrons are negative, and the neutrons are neutral. Yes, the protons are related to the atomic number. Yes, the electrons are in the in the orbitals. But as far as what they are responsible for, protons are responsible for the identity, neutrons are responsible for the isotope, and electrons are responsible for the reactivity. As far as when you get into the periodic tables, the way those particular things worked is I did give partial credit. But if you left off an element, or if you got the element, or if you included an element that shouldn't be there, that counted against you. Now, folks, I wanted to just quickly, I don't think there was as big of a problem in this class, but I want to go over number 5 real quick. Because several people missed it. If you do not know the metalloids, you do not know who's a non-metal and who's a metal. Because the non-metals are to the right of the metalloids, the metals are to the left. And you've got to know that when we start getting into naming. You've got to know that so you know how to do the electron configuration of an ion, because non-metals form a negatively charged ion. Metals form a positively charged ion. So you've got to know that differentiation, and that differentiation is all based on who are the metalloids. The metalloids are boron, element 5, silicon, element 14, germanium, element number 32, arsenic, element number 33, antimony, element 51, tellurium, element 52. And it's up to you. I mean, polonium 84 and astatine 85. I took those because depending upon what reference you use, they may include one of those, both of those, or none of those. So I also don't mind polonium and astatine. But the 6 that you had to have were boron, silicon, arsenic, tellurium, germanium, and antimony. Those were the 6 you had to have. As far as number 6 is concerned, the most missed issue is that a lot of people wanted to include hydrogen in an alkaline metal. Is hydrogen a metal? No, it is a non-metal. And basically, if you were not able to do number 5, then you couldn't do number 8 correctly. Because 8 asked who were the non-metals. Non-metals are to the right of the metalloids. Most people did well on the conversion, which is awesome, because I specifically threw a conversion out to you that I knew wasn't a common set of units to see if you understood what a conversion, how to work a conversion. And I had a few people miscalculate the degrees Celsius. If you did so, please come see me because we need to talk some algebra. And then just to let you know, I kept the last page to 5 points each. So the Rydberg-Balmer was 5, the energy calculation was 5, and the frequency was 5. And folks, you could do the energy and the frequency without being able to do the Rydberg-Balmer. But again, if you did that, the most missed issue was you forgot to pay attention to your units. And I had a lot of people that forgot to convert those nanometers for the wavelength into meters in order to use the energy equation and the frequency equation. Again, the answer key will be placed on the online. Those were just some of the biggest missed issues. Any questions for me? And again, I did try to give partial credit to the best of my ability. But if you scored poorly on this exam, we need to probably chat. I mean, I'll chat with anybody, even if you scored well on this exam. In fact, I'm thinking about giving a quiz for next week where you have to come find my office because only a few of you have come to visit me. And I want to make sure that you know where I'm at because it's going to get tougher. Just from experience, it's going to get tougher. You may not struggle, I don't know, but from experience, it usually gets tougher. Questions? Questions about the top 4 things on that, on the screen? Oh, nope, I'm not taking that off. A little too cool. Okay. So let's move on then. As I go through this next part, what I did is I took what Dr. DeRocher handed me, his PowerPoint that he used, and I basically tried to determine exactly what he went over. So if at any point there's a question, please ask. Because I want to make sure that this stuff is understandable before we continue. So the first thing I noticed is it looks like he may have gone over electron configurations again. So that was good. It was a good review and a good pickup into the next piece, which was electron configurations of ions. Now, I was asked, are you going to have to match definitions and stuff? The answer is no. I'm asking you to know how to use the information. But just like on this test, if you don't know terminology, you can be really screwed up. So you still got to know the terminology, but I'm not going to ask you specific definitions. You got to understand the terms. So the second thing I noticed is that Everybody went over electron configurations of ions. There are two types of ions. There are cations and there are anions. Cations are basically all the cations you need to know are metals. Here comes it. Again, knowing the periodic table. Cations will be metals. These metals lose an electron to become a positively charged ion. Now, when you're looking at the electron configuration of a cation, the electrons that are removed will always be from the highest shell first. In other words, you're looking at that principal quantum number, that n value, that when you're talking 3p6, I'm looking at the 3. It will always be removed from the highest shell and then the highest subshell within that highest shell first. So in other words, you would remove a 5p before you remove the 5s. But you would remove the 5 before getting into the 4d. Anions. These are your nonmetals and metalloids. Your nonmetals and metalloids form anions by gaining electrons, and those electrons are just added to the highest shell, highest subshell. Any questions about electron configuration of ions? Okay, so the next thing he went over is atomic size. And you discussed the trend of atomic size. Size decreases across a period. Here again, if you do not know definitions of periods versus groups on the periodic table, this is a problem. The periods are the rows. The groups are the columns. Size decreases across a period. Now it decreases because the effective nuclear charge, the Z effective, increases. That basically, when we're describing the effective nuclear charge, we're describing how strong is that pull of the positive cation, how strong is that pull of the positive protons to those outer electrons. The stronger the pull, the smaller the atom is going to be. That's what Z effective is. It's the effective nuclear charge. And then the other part is size is going to increase down a group. It increases down a group because of shielding. To quickly illustrate shielding, can I have 4 people line up down the middle? So just stand up if you're on the inside. Okay. So I would like you to just turn around. Y'all stay the same. You 3 of them. Now, can you see the person at the back very well? Why? Because there's people in the way. That is what shielding is. But in this particular case, that shielding is the result of additional ends, additional principal quantum numbers, additional shells. Okay, y'all can have some. It's just the easiest way to visualize what I mean by shielding. Because the front person could not see the back person. If that was a proton, the front person was a proton, and the others were electrons, because of all that shielding, the front person could not effectively interact with the back person. Because it was too much of the way. That is what shielding is. So size increases down a group because you have increased shielding. You're adding on layer and layer and layer of atomic orbitals. And all of those atomic orbitals that you add increases the shielding from the nucleus. Now, when we're looking at these two, if I give you a mixture of everything on the periodic table, the shielding is the more has the greatest impact. Shielding has the greatest impact on size. So if I were to give you 10, element 50, and I were to give you sulfur, element 16, and chlorine, element 17, 10 is going to be the largest because it has the most shielding. Then sulfur is the next largest, and then chlorine. Now, with respect to the Z effective, one of the things we're going to learn today is how to calculate Z effective. Because Z effective plays a huge role in most of the things we're discussing, other than shielding plays the biggest role. But shielding is a visual. We can get into a calculation for our Z effective. Now, my understanding is you also talked about ion size. Basically, when we're looking at an ion size, the cation is going to be smaller than the neutral atom. And the anion is going to be larger than the neutral atom. Now, with this, I also try to give you a picture to help you out. Remember that the size of an atom is related to how well the nucleus interacts with the electrons. That's how the size of everything goes. It's all about how well the nucleus interacts with those electrons. Now, my crazy analogy is that of a family unit. Let's say we have parents or guardians, and they're going to be the nucleus. The parent or the guardian is the nucleus. And then all of the children they work with are the electrons. And let's say our nucleus has a family of 3 electrons. In other words, our guardians or parents have a family of 3 electrons. Now, as a parent, I know personally I tried to spend equal time, or I would. I actually only have 1 kid, so it doesn't quite count. But I would have tried to spend equal time with all 3 of my kids, running them to band, running them to Girl Scouts, Boy Scouts, whatever. I would have tried to spend equal time. Well, the nucleus does the same thing. If it has 3 electrons in the outer shell, it's going to try to spend equal time with all 3. Okay? Now, cations. How are cations made? You take away an electron. So in our particular case, let's send a kid off to college. Very fitting. Now, this nucleus, these guardians or parents, they only have 2 folks to spend time with. And again, they're going to split their time equally. Plus, let's face it, mom starts having a fit because their children are going to college. But what happens is that now that guardian or parent has more time to spend with each other. And because of this whole, I don't know what you're going to call it, they're going to hold them closer. Because they've got more time to spend with them. They're holding them close. So the size shrinks. Because those electrons are being held closer by the nucleus. If we made a +2, that means I've got 2 going off to college. I got 1 left. That 1 gets all of the time. And they're going to be held real close, potentially. So, that's cations. Now, anions, think about an anion. Think about a family unit adopting another child. Now, instead of 3, I got 4 that I'm spending my time with. Am I going to be able to spend as much time with those 4 as I did with 3? No. So they have the electrons have a bit more freedom and they spread out. So the anion size is larger because they have more freedom. Now, again, this Z effective is going to help us understand that. From a mathematical standpoint, we're going to be able to look at some numbers and see this. Isoelectronic series, it just means that all of the atoms have the same number of electrons. It could be a cation and a neutral atom. If the cation and the neutral atom have the same number of electrons, they're considered the isoelectronic. If the anion and the cation and the neutral atom, all 3 have the same number of electrons, they're all 3 isoelectronic. All isoelectronic means is that they have the same number of electrons. And again, we can actually look at Z effective to understand why the cation is going to be smaller than the anions. Question so far? Now, my understanding, the last thing that Dr. DeRocha really went over was this concept. He introduced the concept of ionization energy. I understand that he really didn't get too far into it, but he mainly introduced the concept. Ionization energy. Folks, we actually sort of talked about this back when we did the photoelectric effect. When we were talking about the photoelectric effect, what we were really doing is describing the ionization energy. The ionization energy is the energy to remove 1 mole of electrons from 1 mole of atoms in their gas form to form 1 mole of cations in the gas form. Now, ionization energies are done in a stepwise fashion, meaning we're going to remove 1 mole of electrons at a time. So we have any atom, atom A. If we remove 1 mole of electrons, we make cation A+. That would be the first ionization energy because we removed 1 mole of electrons from a neutral atom. Now, ionization energies are successive. They're in a row. They happen 1 at a time. So the second ionization energy would be the result of the removal of the 2nd mole of electrons. So in other words, we're taking our +1 cation, we're removing another mole of electrons to make a +2 cation. That would be IE2. We can have ionization energy 3. which would take this A2 plus and remove another mole of electrons to make an A3 plus, and so on and so forth. So in other words, when we're talking these subscripts, it's describing where we are in the process of removing electrons. Again, Z effective can help you understand these ionization energy trends too. And we're going to pick up with this today. Any questions over what Dr. DeRocher went over that maybe I have not covered? This was my understanding of what he covered on Thursday. So the goal of today, as I'm going to start with Z effective calculations. As you saw in my storyline, Z effective is huge. The only thing that beats Z effective is that shielding. Shielding is the only thing that can beat Z effective. Otherwise, Z effective is huge. So we're going to start with Z effective calculations. Then we're going to talk about ionization energy trends. How much energy does it take to remove the first electron compared to how much energy it takes to remove the second electron, and so on and so forth. And then I'll briefly introduce electron affinity. I'm not going to spend a lot of time on electron affinity because unlike atomic size, ion size, and ionization energy, electron affinity is a little less predictable. In other words, the trends are not the same. But I still want to at least introduce electron affinity. So Z effective. We will be using what's called Slater's rules to calculate the Z effective for our atoms and ions. Now, when we talk about the Z effective for hydrogen, the Z effective for hydrogen is 1. There's no shielding, and it's just a 1 proton on a 1 electron system. So the Z effective, the effective nuclear charge for hydrogen is 1. To get to helium, we will subtract 0.3 from helium's atomic number. Well, helium is element number 2 on the periodic table, so its atomic number is 2. So 2 minus 0.3 is 1.7. So the effective nuclear charge, Z effective, for helium is 1.7. Now looking here, hydrogen was 1, helium is 1.7. So hydrogen has a smaller Z effective. In other words, the nucleus is not pulling on hydrogen's electrons as well as the nucleus pulls on the electrons that are in helium. So helium is a smaller atom because remember, Dr. DeRocher and I earlier said that as you go across a period, the size decreases. The size decreased because Z effective became larger. The effective nuclear charge became larger. Now, when we start getting into all other atoms, the Z effective is going to equal the atomic number minus the sum the sum of the adjustments. Now, the table that I have pulled up shows you what those adjustments are. So we're going to be looking at a valence electron. A valence electron is going to be the electron in the outermost shell. Or one of the last electrons added. When you are, so basically what we do is say, okay, what is all of the other electrons' impact on this one little bitty electron? And you will notice that group, we're talking about NS, so 1s, 2s, 3s, 4s. In P, 2p, 3p, 4p, so on. In D, 3d, 4d, 5d, so on. In F, 4f, 5f. So you identify the type of electron. Is it an sp electron or is it a df electron? If it is an sp or a df, for all of the electrons in the same shell as the electron we're studying, we would subtract out 0.35. Now, when we get to the ND and S, if the electron is in the same principal quantum number, but it is in a lower L value, then we subtract 1. What does that mean? So let's say I have a 4F electron. All of the other electrons in that 4F will be at 0.35 adjustment. But once we get to the 4D, all the 4Ds would be a 1 because it's in a lower L value. Now, the impact of an electron in N-1. So in other words, principal quantum number -1. If it's an SP, it's 0.85. If it's a DF, it's a 1. And then if we're talking about N equals N-2, N-3, so on and so forth, it's a 1 period. Where N, folks, is the principal quantum number for that electron. Now, to see this in action, we're going to do several calculations. So I want to give you a moment to get all of this written in, because you can refer back to this for the homework. You can that will be available today. So I want to make sure everybody gets a chance to get it written in. And I'm going to keep referring back to this table, but I'm not going to flip back to the table. So you're going to hear me talk through these particular groups and columns. So I'm not going to flip back and forth. Okay, so let's begin with carbon. First thing I'm going to do is I'm going to write out the electron configuration. It's 1s2, 2s2, 2p2. Now, I am going to be evaluating an electron of interest. So when I get to my calculations, I'm not going to take that electron of interest into account. So the electron of interest, if I have it in the P's, I'm subtracting that out. So what I need to do in my calculation is I need to take into account all of the other electrons. No car. Now, I know this looks weird. Carbon is still 1s2, 2s2, 2p2, folks. It's just in order to help you identify which electrons we're talking about, I have removed the electron of interest. That's all I've done is just remove the electron of interest so that I know that which electrons to include in my calculation. So again, I'm including 1s2, 2s2, 2p1 in the actual calculation. So my Z effective is going to equal the atomic number. It is atomic number 6. And then minus the sum for all of our adjustments that we need to make. Now, looking back at our definition, we're talking S and Ps here. So we're looking at this grouping. If it is in the same group, it's going to be a 0.35. And I guess even though it didn't write it, we should probably put 0.35 for this one. It's in the same group, it's 0.35. So in other words, this one is going to be 0.35 because it's in the same peer group, or same shell, same subshell. This one is also going to be 0.35 because it's in the same shell, but a lower L value subshell. And then these two will be 0.85 because they are in an N-1 subshell. So to finish this calculation, it would be 3 electrons times 0.35 plus 2 electrons times 0.85. So the Z effective for carbon is, whoops, I don't know what I did wrong, but I did something wrong. Is 3.25. So what does that mean? If you'll recall, here's our nucleus. We have electrons in the first shell. and we have electrons in the second shell. And I'm gonna just, to make my life easier, keep all the electrons together. So we had four of them in our original. This is the electron of interest. So we took into account all of the other electrons. And what we are describing is the pull on that one electron based on its interactions on shielding and everything else. Questions?
Are we just picking like a random one?
I'll always pick one at the end unless I tell you otherwise. Just pick one in the outermost shell, subshell, unless you're told otherwise. Let's look at fluorine. So fluorine is 1s2, 2s2, 2p5. If I remove my electron of interest, that means that what I'm working with is 1s2, 2s2, 2p4. Following our table, that means these are 0.35 because they are in the same shell, same subshell. And these are 0.35 because they are in the same shell, but just a lower N value or lower L value. And once again, these are in the N-1. So fluorine is element number 9 on the periodic table. So the Z effective would be equal to 9 minus, we have 6 times the 0.35, plus we have 2 times the 0.85. So this gives us a value of 5.2. Fluorine is smaller than carbon because the Z effective for fluorine is greater. So as you go across a period, the atomic size is going to decrease because Z effective increases. No, because if we get into sodium, magnesium, it becomes a 1. Because now it's an N-2. So you have to follow that table. So if it's only 1 shell lower, then yes. But if it's 2 shells or more lower, then it's a 1. Because it increases the amount of shielding that those electrons provide. So what I want to do next is I want to do copper. Copper is 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. If I want to look at the electron in the so here we have 2 options. I'm going to look at that 4s1 electron because it's the electron in the highest shell. You could look at the 3D.
So that means we're gonna have 1s2, 2s2, 2p6, 3s2, 3p6, 3d10 that we're actually looking at. We have to keep in mind what we're working with here. We're working with that 4s1. Okay, so looking at our rules. First thing we do is we have a D. And if you'll recall, again, we're looking at the 4s1 here. So our D would be in the n-1 group, because it would be 4 minus 1, or in other words, the 3D group. So we're going to have to take away 1 for every D electron. Now, looking at our 4s, and we've got our 3p, 3s. Again, those are in the n-1. So for those, we'll be taking away 0.85. For our 2s, 2p, well, that is in 4 minus 2 would get us to our 2s, 2p's. So we would take away 1. And we'll also take away 1 for that 1s, because it's in the 4 minus 3. So copper is element 29. So we're looking at a Z effective of 29 minus, we have 8 times 0.85, plus we have 10, 20 times 1. So we get a 2.2 as the Z effective for copper. Questions? Yes. Because if you go up here, we treat the SPs differently than we do the DFs. So it's because of them being treated differently because of the type of shell and subshell. I should say type of subshell. Okay. So I want to look at copper 1+ real quick. If we have copper 1+, it's 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. That is copper +1 because you remove the 4s because that was the electron in the highest shell. Because I have 10 from the 3D and I have 10 from the 2s and 2p's and 1s. So I added up the superscripts. 2 + 2. If you look right, so let me get up and point. 2 + 2 + 6 is 10, + 10
And those were all treated with a 1. So I just combined them all to make it into one.
This, but why do you have 4S1? Did you take one from the S?
Yes, because it's an anomaly.
Okay.
It's in group 11. And group 11 are your anomalies. Okay. So when I remove an electron to become a cation, it always comes from the highest shell, which is the highest numerical value. So the one that we have to get rid of in the formation of a cation was this 4s1, because that one was the one in the highest shell. Now, if we're looking at the Z effective, for this one, we're going to remove, we're going to subtract a D, because those are the electrons in the highest that are left over that are in the highest shell and subshell. So in other words, in figuring out what we need to add to our calculation, we'll have 1s2, 2s2, 2p6, 3s2, 3p6, 3d9. Looking at our definitions, let's take into account the D. That one is in the same group. So the 3 Ds are the same group. Let me get rid of this first, so I don't have it still there. They're in the same group, so we're going to be using 0.35 for all of these Ds. In the same period, impact of an electron in the same group but lower L value. That would be our 3s and 3p's, because they are in the same numerical N, but they're in a lower L value. So we will be subtracting 0.35 for the 3s's and 3p's. Our S and P's. Now, N minus 1 is equal to 3 minus 1, so it's 2. So we're looking at our 2s, 2p's here. So that's a 0.85. And then we have our 1s. That would be in the N minus 2, because 3 minus 2 is 1. So that's our 1s. And so we would subtract out a whole 1 for those. Again, copper is element number 29. That cannot change. Now we're subtracting out 915 times 0.35 plus 8 times 0.85 plus 2 times 1. Yes. Isn't 6 plus 9, 15? Oh, yes, 17. Thank you. Now see. I always have to reread it myself. Okay, so we're looking at 29 minus. That
And when we get our Z effective, it comes out to be set 14.25. I did this correct. Let me double check. Yep. So folks, the cation, Cu plus, is smaller than Cu because the Z effective is larger. So when we were, this goes back to what Dr. DeRocha was saying about the trend. What I want to look back at real quick is what he said about the trend. Atomic size decreases across a period. We proved that with carbon and fluorine. They decreased across a period because they had an increasing Z effective. And he talked about ion size. Cations are larger than, cations are smaller than their neutral atoms. That is a fact because the Z effective of the cation is significantly larger than the Z effective for the neutral atom. So Z effective helps understand those trends that he was discussing. Questions? You could do this for isoelectronic series and you will find out that the Z effective is the reason for the isoelectronic series and the sizes that he described. So what I showed you is a mathematical calculation. Now, folks, one of the things I did not tell you, if you are removing, let me just say I have one. Sometimes it's just freezing up on me. Let's say I have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, and I could continue going on with that. And let's say I wanted to evaluate the Z effective for a 3D electron. Because you can evaluate the Z effective for every single electron in the atom. At this point, I've just shown you doing it for the valence electron. But technically, you can evaluate the Z effective for every single electron. Now, what I wanted to say is, if you're going to evaluate the Z effective for the 3D electron, it means you can ignore the 4s2 and the 4p2, 4p6, because they are in an outer shell. than the electron of interest. Think about it. Here's your nucleus. Here are your electrons. If I am, whoops. If I want to evaluate this electron right here, for the Z effective, which is the pull from the nucleus, do these electrons have any impact on that electron? No, because they're not in the way. So you're only looking at the electrons that are before that shell. You're not looking at the electrons that come afterwards, because those electrons are not in the way. When calculating Z effective. Okay, I'm gonna have to adjust the quiz as soon as I get back to my office because I had included ionization energy. The only thing related to ionization energy that may be on the quiz is basically the definition of ionization energy or first or second ionization energy, but I will not include trends of ionization energy because I did not get there. What that means is on Thursday, we will be picking up with ionization energy trends. And we will be talking about, and folks, ionization energy trends are going to be related to Z effective again. But we'll talk about ionization energy trends and briefly mention electron affinity, but then folks, we're going to get into the ions. And in Blackboard, there's some extra folders this week. One of them has three of those documents I passed out at the beginning of the semester related to the ions. And the other one has a Quizlet, so you can start practicing your ions that I've actually already prepped for you. Any questions? If not, don't forget about the quiz. Again, it'll come up and then you'll also have a homework due tomorrow. I will see you Thursday.